Assalamu alaikum. This is an overview of the laws of physics that lies behind the production and adjustment of normal and abnormal voice in order to understand the basis of the tests for voice signals and voice analysis. The applied physics behind the following will be discussed: the natural frequency of oscillation of the vocal folds, the Eigenfrequency and the formula, the mechanism of the self-sustained vocal fold vibrations, the Bernoulli effect, the glottal canal non-zero vertical phase difference, the inertive, the mass-like properties of the supraglottal air column, and the vocal fold mechanical properties, particularly the stiffness, the vocal fold contact waveform, and the glottal area waveform, and the glottal airflow waveform and tests. Voice production is essentially an energy conversion process in which the aerodynamics energy supplied by the pressure of the air driven out of the lungs is converted at the glottic level into an acoustic energy by the myoelasticity of the vocal fold tissues. This myoelasticity drives the oscillation of the vocal folds, which essentially modulates the continuous air stream into a series, like a train of air puffs, with a certain rate that is the fundamental frequency of the glottic signals. And this is the essential first part in the voice production. All physical structures, that is to say anything that has a mass, can vibrate if subjected to external forces. So they can all vibrate, and they can particularly vibrate well at a natural frequency, their own natural frequency. If the different frequencies of exciting forces are plotted against the amplitude of vibration, you can see that different frequencies can excite structures to vibrate at varying amplitudes. The peak of the amplitude at which an object can vibrate is its natural frequency, and that varies from one system, one structure, from another. They would vibrate much better at their selected natural frequency, that is to say the eigenfrequency, and they would have a particular way of vibration at this frequency called the eigenmods. So the natural frequency, the eigenfrequency, is the frequency at which these structures would tend to vibrate when subjected to certain external forces. It's much easier to set a system or a structure to vibrate at this frequency than it is at frequencies much lower or much higher. When a complex excitation form with different frequencies are applied to a system, the system would pick up its natural frequency and vibrate at that natural frequency in the particular natural mode, its eigenmode. The motion pattern, the vibration pattern of a system oscillating at its natural frequency, is termed the normal mode or the eigenmode. That's when all parts of that system are moving sinusoidally with that same natural frequency. This natural frequency is described by this formula, in which the frequency would increase with increasing the stiffness of the system or the object, and decrease by increasing its mass, its vibrating mass. The frequencies are dependent on the way the mass and the stiffness are distributed within that structure or that system. In a complex structure or a system with different parts or segments with different eigenfrequencies and different eigenmode of vibration at these frequencies, if this structure is set to vibration, the different segments would vibrate preferentially at their eigenfrequencies. Some of these segments would vibrate in phase with each other, and some would vibrate out of phase. So you had different or several eigenfrequencies and eigenmodes in the same structure. And the outcome, the final outcome, will be a superposition of the independent characters of the vibratory pattern of each of its segments. That's exactly the case with the vocal folds. Vocal folds are heterogeneous structures with several layers of material with different physical and mechanical properties, including the muscle core and lamina propria with 3 different layers, and the cover, and each of these has a different physical properties. In addition, the muscles of the larynx can change the elasticity and the tension of the vocal folds, and also its geometry, the geometry of the vocal fold, including the length, the depth, the thickness of the contact area, the contact mode itself, that is the vibrating mass of the vocal folds. That's why the vocal folds should be expected to have an infinite number of eigenfrequencies and eigenmodes. Adjustments of the vocal folds eigenfrequencies is largely achieved by varying and changing the stiffness and the tension applied on the vocal folds in the anteroposterior direction. This is primarily controlled by activation of the cricothyroid muscle. The fundamental frequency of the voice during a certain moment would depend primarily on the frequency of the vocal fold eigenmode at this particular moment that were excited. The eigenmode and frequency in turn depends on the vocal fold geometry, the configuration of the vocal folds, and the length, depth, and thickness of the vibrating mass, together with the stiffness and the stress conditions of the vocal fold. And because these will keep on changing all the time, there will be theoretically a huge number of eigenmodes and frequencies to choose from during voice production. However, it was found out by computer modeling or physical modeling using excised larynges with high-speed cameras that only few dominant eigenmodes, the lowest of the eigenmodes, can actually play a substantial role in the production of voice. Using the computer models or using physical models with larynxes, sometimes canine larynges, this was illustrated well that a combination of only 2 eigenmodes can capture more than 95% of the variance of the vocal fold vibration in normal phonation and more than 70% of the variance during irregular vocal fold vibration. The 2 dominant vocal fold eigenmodes during phonation are termed X10 and X11. These are 2 different modes of motion or vibration. The first one, the X10, presents the lateral to medial oscillation, which is responsible for the opening and closing of the glottis during phonation, and it's actually responsible for the voice production by allowing puffs of air when the glottis opens to pass through it, producing voice. The X11 is another pattern of movement with convergence and divergence of the glottal canal here. You can see that the lower ends of the medial ends of the vocal folds always lead the upper ends during closure and opening of the glottis canal. And this pattern of movement allows the transfer of aerodynamic energy into the vocal fold tissues to support phonation. This is a closer look at what happens during phonation with the self-oscillation of the vocal folds. This diagram describes 3 different eigenmodes during phonation. We start with the last 2 because these are the dominant eigenmodes that produces more than 95% of the movement during phonation. This one is the medial lateral type of movement. You could see this thin line is the neutral position, and the vocal folds can move medially, the interrupted line, and laterally, the thick line, and this would allow closure and opening of the glottic canal, allowing puffs of air to pass and phonation to proceed. This is the principal Eigen mode or pattern of vibration. The other one is when the lower ends of the vocal fold leads the upper end in movement. So it's a rotational type of movement with the lower end leading, forming a divergent glottis, and also leads it when it is opened, forming a convergent glottis. So you could see that the lower end and the upper end of the vocal folds are not in phase during this pattern of vibration. The lower end always precedes the upper end. The third type of motion during phonation is up and down movement, superior to inferior. And there is a considerable argument about whether this is a separate pattern of vibration or actually just a part of these two. As you can see, during these two patterns, there is some leveling up of the upper end of the vocal fold. When the tissues move, there will be some heaping of the tissues in both these modes of vibration, particularly this mode of vibration. It's just a part of the movement that the superior part of the vocal folds will raise up and the inferior part will also raise up during phonation. Or it can be considered a separate type of phonation with an upwards and downwards movement of the vocal folds. Not only the vocal folds has eigenfrequencies and modes, other laryngeal structures can also vibrate at certain frequencies and respond to vibration applied externally, for example through the neck. Below 100 Hz, the vibrations of the ventricular folds are much higher than the vibrations of the vocal folds itself, because the ventricular folds are assumed to have eigenfrequencies and modes around 70 Hz. The arytenoids and the aryepiglottic folds can also vibrate at their natural resonance frequency of 50 Hz. We are watching here the surface mucosal wave of the adducted vocal fold bodies. Note that there is a phase difference between the superior and the inferior parts of the vocal fold cover, the medial surface of the vocal cords that meets in the midline, and that the surface wave propagates from inferior to superior. The inferior part of the vocal folds leads not only during the conversion of the vocal cords closer together in the midline, but also during diversion of the midline as well. Because of the difference in the pace between the inferior and the superior parts of the surface of the medial ends of the adducted vocal fold, when the vocal folds start to open up at the inferior part, it's still closed and maintain closure of the glottis at the upper part. The difference in the pace between the inferior and the superior parts of the surface of the adducted vocal folds is termed vertical phase difference, the vertical phase difference of the vocal folds mucosal wave. And being a non-zero value, it provides asymmetry in the intraglottic air pressure. This is essential for maintaining self-driven oscillation. The phase difference is in turn affected by the vertical thickness of the medial ends of the vocal folds and also by the medial bulge of the inferior part of the medial adducted vocal folds. A similar phase difference is also noted during the conversion and the diversion of the medial ends of the surface of the adducted vocal folds. Much like the phase difference between the superior and the inferior parts of the surface of the medial parts of the vocal folds, the anterior parts of the vocal folds also lead the posterior parts during conversion and diversion, giving rise to what can be seen as a zipper-like closure and opening of the glottic canal. The myoelastic properties of the larynx complex interaction with the stream of air puffed through the larynx from the lungs. This complex interaction and the myoelastic theory forms the basis of our current understanding of how the vocal folds oscillation would produce the voice signal, the acoustic vibrations at the laryngeal level. It was suggested by Bernoulli in 1950s, and he also suggested that the mechanism of sustaining the oscillation is the Bernoulli effect. It's now accepted that several other mechanisms can be used to sustain the oscillation, and that in fact the Bernoulli's effect may have a secondary role. The mechanism should induce asymmetry in the intraglottal canal pressure, and this is the driving force for sustaining the oscillation. We shall go through the three possible mechanisms to explain the sustaining oscillation: the initial Bernoulli effect, the alternating convergence and divergence of the glottis, which would produce variation in the intraglottal canal pressure, and the effect of the inertia of the supraglottic air column on sustaining self-oscillation. The condition to have a self-sustained vocal fold vibration is to have asymmetry in the intraglottal canal pressure, the pressure in the intraglottal canal in here. If there is asymmetry providing positive pressure in the opening phase, that would help getting the two vocal folds apart, and negative pressure during the closing phase that will pull the medial ends together to close the glottis. This is the condition for self-sustained vocal fold vibrations. The intraglottal canal pressure equation is here, and as you can see, the intraglottic pressure is dependent on two entities. The first entity is this, and this is the second entity. The first entity is basically the difference between the subglottic and the supraglottic pressure. If there is more pressure in the subglottic area, it's going to drive air through the canal, but this is multiplied by a certain factor reflecting the configuration of the glottis. If you have a convergent glottis, like in the opening phase, with a larger entry, this is A1, the surface area of the entry into the canal, and A2, the surface area of the exit to the canal. If this is the case, this fraction will be smaller than 1, and you will have positive pressure in the canal. If it is the reverse, when you have a larger A2 than A1, then this factor would be negative, and you would have negative pressure in the canal. The second entity is the supraglottal vocal tract pressure. So as we can see, the condition for having an asymmetry in the intraglottal canal can be fulfilled by these two mechanisms: the alternating convergent and divergence of the glottis, and the second mechanism is the inertive properties of the supraglottal tract that determines the second entity, and we shall go through these in this presentation. So we start with the Bernoulli effect. This was the initial proposed mechanism for self-sustained oscillation, with repeated cycles of opening and closing of the glottis due to the build-up of pressure when the glottis is closed. Above a certain limit, this pressure is going to drive the vocal folds apart, and air would escape, and this would create a stream of air, a jet of air in here with high velocity that is going to create a negative pressure around it, and this would close up the vocal folds again, and a new cycle is going to start with a build-up of the pressure, driving the air after a certain limit of pressure up. This would create the Bernoulli effect again, and the vocal folds would close once more, and a new cycle would again start. But there are now suggestions that the Bernoulli effect is not really necessary for the sustained oscillations, and that it fails to explain some aspects of the vibration cycle of the glottis. Without a vertical phase difference in the medial ends of the vocal fold, the vocal fold surface during opening and closing would be identical. This symmetrical flow pressure inside the intraglottic canal and there would be a loss of the asymmetry of the intraglottal canal pressure, and consequently a zero transfer of energy from the glottic canal into the vocal folds. The second proposed mechanism to explain the self-sustained oscillation is this: the alternating convergence and divergence of the glottis due to the vertical phase difference in the vocal fold vibration. The lower end of the vocal fold medial part always leads the upper end, either during the opening phase or during the closing phase. There's always a phase difference between the lower and the upper end, and this creates enough asymmetry in the intraglottal pressure to drive the vocal folds widely apart during the opening phase and closer together during the closing phase. Important to know that this property, this phase difference in the vertical phase difference in the medial ends of the vocal fold, is actually an intrinsic property of the vocal folds itself due its geometry and its mechanical properties of the material forming the vocal fold. So it's an intrinsic property of the vocal folds itself. And now let's see how this proposed mechanism can actually explain the self-sustained oscillation. Back to the equation of the intraglottal canal pressure, and we see the two entities here that determines the value of the intraglottal pressure. And let's concentrate on the first entity itself, and for now try to neutralize the second entity here by assuming that the pressure in the vocal tract is closer to zero. So this is going to remove this second entity, and also will make the difference between the subglottic and the supraglottic pressure equals only to the subglottic pressure itself. So the equation will now be reduced to this. And let's see how this can provide the asymmetry in the intraglottal pressure during the vibration cycle. So when this equation is applied during the opening phase of the glottis cycle, when the geometry of the glottic canal is convergent with a larger entry area than an exit area, this fraction would be smaller than 1. So this entity would be positive. The positive intraglottic pressure would help in driving the vocal folds apart during the opening phase of the glottic cycle. And the exact opposite would happen during the closing phase of the vibratory cycle, because the configuration would now be divergent with the lower end leading the upper end. And because of this divergence, the area of the exit is larger than the area of the inlet, and this will produce a number here that is more than 1. So this entity will be negative, providing a negative intraglottal pressure. A negative intraglottal pressure in here would help in getting the vocal folds medial ends closer together towards the midline, thereby closing the glottis during the closing phase of the glottic cycle. This graph sums it all. It shows the asymmetry in the intraglottic pressure, resembled here with this thick black line. It is positive in the opening phase of the glottic cycle, when the geometry of the glottic canal is convergent, like in here, and it is negative in the closing phase of the glottic cycle, when the geometry of the canal is divergent, as in here, and it is 0 when the glottic entry is equal to the glottic exit area in here. As you can see, the glottic area entry is shown up here. So this is always more than the glottic exit area in the first half of the cycle in the convergent opening phase. And the reverse happened in the divergent phase. The exit surface area of the canal in here is demonstrated here in this dotted line is always more than the inlet area. So this would summarize the whole findings. The intraglottal pressure is positive during the opening convergent phase, and it is negative during the closing divergent phase. And note that the maximum positive pressure is at the beginning of the cycle, the very beginning of the opening cycle, when and excess pressure is required to push the medial ends of the vocal folds apart, and it's also a maximum negative at the end of the closing phase when some negative pressure is required to abruptly close up the glottis. We now move to the other mechanism that was proposed to explain the self-sustained oscillations of the vocal fold. This third mechanism is the mechanism of the inertive, the mass-like properties of the supraglottal air column, the air column above the glottis in here. And as you can see from the previous equation, this is basically the second entity in here, the entity of the pressure in the supraglottal vocal tract. The equation shows that the intraglottal pressure is dependent on two entities, and for now let's try to ignore the first entity that we have been through it with the second mechanism of the convergence and the divergence of the vocal fold canal, and concentrate on the second entity. To do this, let's assume that the inlet area A1 and the exit area A2 of the glottal canal are equal. This will make this fraction equals to 1. 1 minus 1 equals 0, and multiplied by this, it will end up as 0 as well. So the intraglottal pressure will depend basically only on the supraglottal vocal tract pressure. So now we need to examine what determine the pressure, the input pressure in the supraglottal vocal tract. It's actually two things in here: the inertia of the air column above the glottis up to the lips, and the rate of the glottal flow, the change in the glottal flow over time in here. That is to say, the glottal flow through the glottis over a time period. The inertance of the vocal tract is in turn calculated from this equation and gives almost a fixed value because it's dependent on the density of the air, the length of the air column in the vocal tract, which is about 17 centimeters or so from the glottis to the lips, and the cross-sectional area of the vocal tract above the glottis, which is about 3.5 centimeters square or so. So this value is almost fixed, and the input pressure into the supraglottal vocal tract is dependent on this, on the change in the glottal flow rate. On the glottal flow increases rapidly, this is going to be increased, and when it decreases rapidly, this is going to decrease. And this would be reflected through the pressure Pi into the Pg, which is now equal to it. So this change in the glottal flow rate is basically dependent on the difference between the subglottic pressure and the supraglottal pressure. If this is increased or is increasing in the opening phase, then this value is going to increase and increase the input pressure, and the intraglottal pressure would also increase, and this is going to drive the vocal ends apart during the opening phase. And the exact opposite is going to happen in the closing phase when the rate of the change in the glottal flow here is reduced and becomes negative, and this will be reflected in the input pressure and consequently on the intraglottal pressure, and this is going to drive the medial ends of the vocal cords closer together because the pressure would now be negative. Now again, this graph sums it all. It sums up the changes in the intraglottal pressure that is due to the inertance of the vocal tract air column. We have been through a similar graph for the changes of the intraglottal pressure due to the convergence and the divergence of the glottal entry and exit surface area. And as we can see here, the intraglottal pressure is again positive in the opening phase when there is a positive pressure in the intraglottal canal, and negative in the divergent and closing phase when the intraglottal canal is below 0, and it reaches a 0 point between the changes in the opening phase and the changes in the closing phase. So we have been through these two mechanisms of convergence, divergence, and the inertia of the supraglottal air column, to try and explain why the vocal folds can self-sustain oscillations. Back to the equation, we have seen that there are two entities. One of them is the pressure in the supraglottal vocal tract, which is dependent on the inertia and on the change in the glottal flow rate, and the other entity is dependent on the convergence and the divergence of the glottal canal entry and the difference between the subglottis and the supraglottis pressure. So these are the two mechanisms that can explain how the intraglottal pressure have an asymmetry, being positive in the opening phase and negative in the closing phase. Thereby it drives the vocal fold medial ends apart while the glottis is trying to open and suck them together closer to the midline when the glottis is trying to close up. In fact, we have taken the two mechanisms one at a time by trying to neutralize the effect of one side while focusing on the other. But in reality, the two mechanisms would act together to provide the required asymmetry in the intraglottal pressure that is required for self-sustaining the vocal fold oscillations. All objects or structures have an inherent mechanical property that is intrinsic in the material of the object or the structure. It's the way it resists deformation, like stretching or compression, when a force is applied to it. Stress is defined as the force applied to the object to cause its deformation, either stretching or compression, divided by the surface area of the object or the structure perpendicular to the direction of the applied force. Strain quantifies the amount of the deformation, either the stretch or the compression, after applying certain stress. So stress is mathematically the force over the surface area, and strain is the amount of deformation divided by the whole length. So it's a relative deformation. The ratio between stress applied to an object and strain, the result of the application of the stress, is called the Young's modulus and reflect the elasticity of the material of that object or structure. Young's module is the stress divided by the strain. Here are some examples of the elastic modulus of several materials together with their densities and the ultimate strength, which is the point at which the material would break. Large elastic modulus value would tolerate stress better and show only little strain, little compression, or little stretch when a certain stress is applied to it, compared to materials of very low elastic modulus, like polystyrene, for example, in which the small elastic modulus means that the stress can produce large strain. Stress on a rubber band would produce large strain, like maximum stretch. The same amount of stress, if applied to steel, would only produce a very small deformation, change in the length of the steel bar. In between steel and polystyrene, there are other materials, including, for example, bone, including glass, including concrete, and different other materials in between the two extremes. This is a typical graph of the stress on the y-axis. Again, is the strain on the x-axis relationship for the materials of the vocal folds, demonstrating how forces, ascending magnitude of forces on the vocal fold, can cause stretching or compression of the vocal fold's heterogeneous tissues. The slope of the curve, the tangent line on the slope of the curve, quantifies the stiffness of the vocal fold, how it resists deformation, stretching, or compression. The plot shows that the vocal folds exhibit three mechanical properties. The stiffness is not linear, it's a nonlinear, as we have just discussed, and the strain is not equal in all directions, that's another property. and the vocal fold has also some viscoelastic behavior, as we are going to discuss in the next few slides. Again, frequencies of the vocal folds increases with the increase of either the stiffness of the vocal fold or the stress, the tension applied on the vocal folds during phonation. This describes the relationship between the stress applied on the vocal fold, the force or tension applied on the vocal folds, and the strain, the amount of elongation of the vocal folds under the influence of the force. You would expect an increase in the length of the vocal folds with the increase in the tension of the stress, but this increase is not always linear. In the case of the vocal fold tissues, it's actually non-linear. As you can see, it's like a curve with a considerable change in the length of the vocal fold with only a small changes in the tension in the early parts of the curve, and in the later part of the curve you would need a considerable amount of tension to increase the vocal fold length only a small bit. This property of nonlinear material of the vocal fold explains why in the early parts of this curve, when the vocal folds are only slightly elongated, that the stiffness of the vocal fold is more important than the tension applied. But in the later part of the curve, both the stiffness and the tension or the stress are equally important. The first mechanical property is the nonlinear stiffness. Stiffness here is the tangent line to the curve, to the stress-strain curve. You would see in the initial segment of the curve, the slope is very gradual. You need to stretch the vocal folds a lot in the strain direction with only a very small amount of stress, of applied force. There will be a small amount of stress for a large amount of strain, whereas in the other segments of the vocal fold cycle, towards the end of the cycle, large amounts of stress is required to produce small amounts of strain. So that's why it's a nonlinear stiffness. Because of this nonlinear stiffness of the vocal folds, changing the vocal fold length would also lead to changes in the vocal fold stiffness. If the material is linear, if the vocal fold material is linear, then there would be no such thing like increase in the stress when the length is increased. This property, this nonlinear stiffness, can therefore be used to regulate the vocal fold stiffness and tension through vocal fold elongation or shortening. This is important in the control of the fundamental frequency of the vocal folds vibration. The second mechanical property is the anisotropic stiffness. That is to say, the stiffness of the vocal fold tissue is not uniform in all directions. The stiffness is much higher in the anteroposterior direction than it is in the transverse direction. The transverse direction is much easier to move the vocal folds in the transverse direction because of the decreased stiffness compared to moving it in the anteroposterior direction. It has something to do with the anteroposterior alignment of the collagen fibers, the elastic fibers, and the muscle fibers in the anteroposterior direction. The Young modulus in the anteroposterior direction of the cover layer is more than 10 times that of the transverse plane. We know that a higher Young's modulus would mean better toleration of stress. There will be small amount of strain with a higher modulus in the anteroposterior direction than it is when the much smaller Young's modulus in the transverse direction. This anisotropic stiffness of the vocal fold has two important applications. This stiffness facilitates the medial to lateral motion of the vocal cord in the transverse direction, and also helps in completing the glottal closure during phonation, as we shall see later. These are the two properties related to the non-uniform distribution of stress in the vocal fold material. The third property of the vocal fold stiffness is its viscous behavior. You can see here that the stress strain curve for loading of the vocal fold, stretching it or compressing it, is different than the graph while unloading, when it is returned back to its neutral position. The stress is typically higher during the loading than it is during the unloading. This is basically due to the viscous behavior of the vocal fold material. Now we explore how the vocal fold stiffness, that's the mechanical property of the vocal fold, affects another mechanical property, that is the natural vibrating frequencies of the vocal folds, its eigenfrequency. All structures or objects, including the vocal folds, have a natural vibrating frequency. These are the frequencies at which the structure would tend to vibrate if subjected to a certain applied force. These frequencies, the natural vibrating frequencies, depends on the vibrating mass of the structure and the stiffness of the structure, and how the mass and the stiffness are distributed along the geometry of the vibrating object or the structure. So mass of the structure, stiffness, and how they are distributed in the structure itself geometrically. Generally speaking, a stiffer structure, that is higher elastic modulus for a structure, would tend to have to increase the natural vibrating frequency of that structure. And finally, the other way the vocal fold stiffness can modulate and adjust the voice produced by the vocal fold is through the effect of the anisotropic stiffness on the glottal closure. The anisotropic stiffness of the vocal fold optimizes the way the vocal folds closes during phonation. The way the fibers are aligned in the anteroposterior direction improves the glottal closure, and also the way the lamina propria has these fibers is between the core of the vocal fold, the muscular part, and the surface. The superficial position of the aligned fibers also improves the vocal fold glottal closure. Even the epithelial layer, the envelope of the vocal fold, the stiffness of this epithelial envelope also improves the glottal closure and improves the duration of the glottic closure and allows vibration for a considerably longer closed period. The vocal fold depth, particularly of the medial ends, and the contact mode of these medial ends can modulate the vocal fold vibration frequency, the F0. This F0 can be increased by the increase of the extent and the duration of the vocal folds contact, and also by increasing the depth of the contact, the depth of the medial ends of the adducted vocal folds. So what are the factors that this vocal fold contact pattern depends on? Primarily the degree of the vocal fold approximation by the adductors, the glottal channel geometry, its extent, its depth, and the duration of the contact, the subglottic pressure, and the vocal fold's intrinsic stiffness during adduction. Changes in any of these parameters can influence the fundamental frequency by affecting the vocal fold contact mode. When the medial ends of the adducted vocal folds are thin, they can be easily pushed apart by the subglottal pressure. As a result, the glottis may never completely closes during vibration, producing a weak and breathy voice. On the other hand, increasing the vertical thickness of the medial ends of the vocal folds during phonation provides a better closure that can resist the glottis opening effect of the subglottal pressure. Also, increasing the thickness would increase the phase difference in the pace between the inferior part and the superior parts of the medial ends of the vocal folds, and this would produce a longer closed phase of the vibratory cycle. Because of this nonlinearity in the vocal folds stiffness, the increase in the high subglottic pressure can actually increase the vocal fold stiffness. The increased vibration amplitude driven by the high subglottic pressure would lead to an increase in the stiffness of the vocal folds and also the fundamental frequency. So this combined effect of the contact mode of the vocal folds and the nonlinearity of the vocal fold stiffness can lead to an increase of about 40 Hz in the fundamental frequency if the subglottic pressure is increased. There are obvious problems about obtaining just a single measure of the fundamental frequency. The fundamental frequency would keep on changing very rapidly and quite widely during voicing of even a simple vowel. The usual is that we would obtain the idea about the fundamental frequency from a longer period of time over which we can estimate the changes in the fundamental frequency during this time period, get an idea about the range of frequencies used, the average frequencies, the mean and the median and the percentiles, and also the distribution of how often we use certain frequencies lower or higher than the median. There exists a huge range of what is considered normal because of changes with the fundamental frequency with age, gender, emotional state, the communicative intent, the mood, and the personality of the speaker. The changes in the fundamental frequency with age and gender can be partially explained by the changes that happen in the vocal folds in terms of opposing factors, increasing the stiffness of the vocal fold with time, and also the effect of the increase in the vocal fold length and mass with time. In the children, the fundamental frequency is usually high with a very short vocal folds and small vocal fold mass. With increasing stiffness, length, and mass, things start to change. This is a graph of the fundamental frequencies of males with time and females over the years. You could see a steep decrease in the fundamental frequency in men after the age of about 10. There will be a significant drop in the fundamental frequencies to below 150 or so, and then a gradual increase over time with reaching somewhere around 150 by the age of 60 or 80. In the female, the decrease in the fundamental frequency with time is much milder, no much change between 20 and 40 years, and then a gradual decline in the fundamental frequency before rising up again towards the age of 70 or 80. We now move to the glottal area waveform, which registers changes in the glottal area. The glottal area is the area in between the two vocal folds during the whole of the vibratory cycle. This is the black area in here. Changes in this area during a vibratory cycle would be reflected in changes in the airflow and consequently in the voice signal. The rapid changes in the glottal area, the glottal opening during phonation, can be detected and registered by the use usually of electrolaryngography, electroglottography, or sometimes by high-speed cameras for photoglottography. These changes, presented in the form of a waveform, can then be analyzed not only to measure the duration of the glottal opening and close phases, but also the speed with which such changes can occur. We'll also go through the effect of such changes on the voice source harmonic spectral slopes with examples of normal, breathy, or pressed voices, and we'll end up with the factors modulating the glottal area waveform. This upper trace shows a typical glottal area waveform during phonation as obtained from an electrolaryngogram. It shows the changes in the glottal area when the vocal folds are coming closer together to close up the glottis before they start to peel away from each other to open up the glottis in the later part of the vibratory cycle before the cycle repeats itself again. The speed of such movements of the vocal folds to close and to open the glottis is not uniform. They accelerate while closing and they decelerate while opening, and these changes can be seen from the lower trace here, which is a time derivative of the glottal area waveform. When there is acceleration in the movement of the vocal folds to close the glottis, it shows a high positive peak in here. This positive peak is used to mark the start of the closing phase. And when they slow down while getting apart to open up the glottis, there will be a small dip in here, much smaller than the positive peak, and this would mark the end of the closing phase and the start of the opening phase of the vibratory cycle. So here you could see that the glottal area waveform is divided into an open phase when the vocal folds are close together and an opening phase when they are apart. These two phases can be further subdivided into a closing phase when they are attempting to close before achieving maximum closure, and an opening phase when they are getting apart from each other before achieving opening of the glottis during phonation. We'll try to add some more details in here. This is again the typical glottal area waveform. This is the real signal of a glottal area waveform, and this is a schematic glottal area waveform. This is the time derivative, how the movements of the vocal folds can accelerate and decelerate, and this is a graph of the glottal airflow during the same vibratory cycle. To this we would add the changes in the configuration of the vocal folds during certain moments of the vibratory cycle. Starting with here in the closing phase of the vibratory cycle, it starts with the lower lips of the vocal fold medial ends moving medially to meet each other before the upper lips can follow later to close up the glottis completely. This is due to the phase difference between the lower lip and the upper lip. This would mark number 1. And we're still in the closing phase here. You would see this positive peak and the speed of the movements of the vocal folds during closure, giving the abrupt closure segment in here, this very rapid closure. And this would be marked as number 2. And then number 3 is achieved with maximum closure of the vocal folds together to close up the glottis. So this 1, 2, and 3 are the closing phase of the vocal folds. Between 3 and 4, the vocal folds would remain closed. So this is the closed phase. And then starting from 4, the vocal folds will start to peel away from each other, again with the lower ends of the vocal folds starting and the upper ends following a bit later. At one moment in here, there will be deceleration and the movements, the speed of the movements of the vocal fold. You would see how the opening up is much slower than the closing up, which is very abrupt. The opening up is very gradual and it decelerates at one point in here. This would mark number 5, and number 6 would mark the complete opening up of the vocal fold and the start of the passage of the air from the subglottis to the vocal tract. So this would mark from 4 to 6 the opening phase, and then from 6 till 1 there will be the open phase until it starts all together again. So these are a way of describing the vocal folds movement in closure and in opening up of the glottis during one vibratory cycle. Here we would see synchronized information obtained from photoglottograms showing the glottis from above, and glottal area waveform obtained from an electroglottogram, and the time derivative of the electroglottogram showing the acceleration or the deceleration of the speed of the movement of the vocal folds while closing and opening of the glottis. In the start of the closing phase, the glottis is still open. You can see some glottic area in there, but the vocal folds are starting to get closer together. And you can see from the traces here that the closing phase had not yet started, and the positive peak has not been reached yet. This positive peak would describe the abrupt closure of the vocal folds and the start of the closing phase. It would be reached in here, and this photographs there, the vocal folds have now closed the glottis. You could see this segment of rapid change in the glottal area waveform and the very high positive peak in the time derivative. And then the closed vocal folds would remain closed for some time before starting to open up again in here. This would mark probably the end of the closing phase, when there is deceleration and the movements of the vocal folds to peel apart, opening up the glottis in this frame in here. And then progressively the opening phase would continue, opening up the glottis further until the open phase is achieved here. You can see open glottis, and we are in this area of the glottal area waveform and its time derivative. Identifying the exact point of the start and the end of the closed phase and the start and the end of the open phase is important in measuring the open and the closed quotients of the vibratory cycle. This can be straightforward if you have a clear glottic area waveform trace like this, with its clear derivative, the time related changes in the glottal area waveform, with a positive peak in here reflecting the rapid and the abrupt closure of the vocal folds, and the gradual opening up of the vocal folds with some deceleration here, giving this dip. If that's the case and you have the positive peak and the negative dip, then you could mark the start and the end of the closed phase and the start and the end of the open phase of the vibratory cycle. But that's not always the case, particularly in some cases of dysphonia, when it is difficult to identify this dip. In most cases, you can still identify the positive peak. There are three other ways of measuring the start and the end of the open and the closed phases. Two of them would depend on the threshold between the minimum and the maximum amount of the glottal area. If you go from the minimum to the maximum 35% up, then you would have a straight line here that marks the start and the end of the closed phase, and from here till the other cycle you can have the start and the end of the open phase. You can have this line at the 35% level from the bottom, or you can have it at 50%. This was proposed by other researchers to have either 35% or 50%. There is a fourth way of measuring the start and the end of the closed and the open cycles, and this is to use the positive peak here, which is commonly present in most traces, to mark the start of the closed phase. But to mark the end of the closed phase by measuring a 0.3/7 of the distance between the maximum and the minimum. This is about 42%. So a 0.42% would mark the end of the closed phase and the start of the open phase. So these are the four ways of measuring the moments for closing and opening of the closed phase and the opening and the closing of the open phase. The duration of the open phase in relation to the total duration of one vibratory cycle gives the glottal open quotient. This has its effect on the voice source spectral slope. If this ratio lies between 0.4 and 0.7, as in normal voices, if it is less than 0.4, it usually indicates a pressed voice, and if it is more than 0.7, it's associated with a breathy and weak voice. This voice source spectral slope graph comes from the fact that the harmonics produced by the voice source changes as the frequency increases. This rate of change of the harmonics when the frequency increases, gives the spectral slope. The lower harmonics here, the lower frequencies, are affected by the increase in the glottal open quotient. If you have a high glottic open quotient, like more than 0.7, then you would get a higher dominant first harmonic and a breathy and weak voice. A typical glottal cycle will start with the closure of the vocal folds. This is the closed part of the cycle, followed by an open part, and then the cycle repeats itself. The duration of time spent by the vocal folds in a completely adductor position and an open position are important in determining the quality of the voice. The major adductor of the vocal fold is the lateral cricoarytenoid muscle, helped posteriorly by the interarytenoid muscle. The small mid-glottic gap is also closed by the action of the thyroarytenoid muscle, the vocalis part of the thyroarytenoid muscles. If there is a disorder that disrupts this adductor mechanism of any of these three muscles, a persistent glottic gap during phonation may cause the voice signal to be abnormal. There will be an open phase during phonation that is a little bit longer than it should. It shouldn't be more than 70% of the whole cycle, but if there is a persistent gap due to the weakness of any of these three muscles, then the air would tend to escape through this gap with a longer opening phase and a shorter contact phase. This continuous stream of airflow can be rapid and can cause turbulence, and sometimes if this is extreme, each vocal fold can vibrate at a different frequency, and this would lead to biphonation, a voice containing two distinct fundamental frequencies. To illustrate this further, these are traces of glottal area waveforms from a patient with vocal fold palsy before and after medialization procedure. Before the medialization procedure, you could see the short closed phase and short contact quotient. The contact quotient for this patient was 28 point something compared to the usual 45 or 46% contact quotient. After the medialization procedure, things improved. The voice is now better and no longer breathy and weak. The contact quotient here has improved to 48%, and there is a longer contact period, longer closed phase, and a shorter open phase. We have noticed how a weak or a delay activation of the thyroarytenoidus muscle can produce a long open phase of the glottic cycle with a longer glottal open quotient, more than 70%. On the opposite, if the thyroarytenoidus is overactivated, it can produce a tighter vocal fold approximation during phonation and a shorter open phase. The glottal open quotient would be less than 0.4. The open phase in relation to the total duration of the cycle would be less than 40%. This would give rise to a pressed voice rather than the breathy voice if the open phase is longer. The pressed voice is often characteristic by a second harmonic that is stronger than the first harmonic. The H1 minus H2 would be negative, and this would produce a pressed voice. Somewhere between these two extremes of a breathy voice and a pressed voice is the modal voice or the modal register, which is more commonly used in phonation, characterized by regular vibratory cycles and a rapid closure of the vocal fold with a more gradual opening of the vocal fold. The opening phase of the glottis would be between 40 to 70% of the glottal cycle. The rapid closure of the vocal folds would produce a harmonically rich voice. This modal voice is produced by the activation of the lateral cricoarytenoid, the interarytenoid, and the thyroarytenoid muscles. They would produce a large medial surface thickness and good contact between the vocal fold medial edges, and probably low anteroposterior stiffness of the vocal folds. This would produce a large vertical phase difference between the medial ends of the vocal folds, an appropriately sized closure quotient or open quotient of the glottis, and a small flow rate and strong harmonics. Vocal folds contact waveform can be captured and registered by electroglottography. Understanding the factors that can influence and modulate the contact mode would be useful in the analysis of the results of the electroglottography and other things, including the glottal area waveform with its open and closed phases, and the glottal flow waveform with its time derivative, and also the voice source spectrum with the spectrum of low frequencies and high frequencies portions. Another useful index that can be extracted from the glottal area waveform is the contact quotient, which reflects the duration of the time the vocal folds are in good contact in relation to the time of the whole cycle. This can be measured by having a line at the 70% from the maximum closure or 30% from the minimum closure, and at this point in time you can drop a line here to measure the time. In here, this time in relation to the whole cycle will give the contact quotient. In normal males and females, it would be somewhere between 43.8 and 46.3%, and this would correlate well with the vocal intensity positively. So the higher this is, the higher the vocal intensity. In things like vocal cord palsy, this contact quotient would drop to 20 something rather than 43 or 46. Contact quotient can be increased by good level of vocal training. It can also increase in some pathologies affecting the vocal folds, like rhinx edema, for example, and in some muscle tension dysphonias when the voice is pressed. On the other hand, the contact quotient would be reduced if there is reduced contact between the vocal folds, as in vocal fold palsy or in presbylaryngeus, or in some muscle tension dysphonias associated with weak and breathy voice. What is also of importance is the standard deviation of the contact quotient between different cycles, as this would generally reflect an increase in dysphonia due to the difficulty in controlling the degree of contact from one cycle to the other. The glottal flow waveform, or the flow glottogram, is a representation of the airflow during each glottal cycle. It is derived from the oral airflow signal using inverse filtering, and from this, important voice source values can be derived. We'll go through how to estimate the glottal flow waveform from glottal inverse filtering, and the relation between the glottal flow waveform and the glottal area waveform. We'll go also through the effect on the voice spectral slopes with examples from modal, breathy, and pressed voices. Indirect techniques are used to estimate the glottal flow. Why indirect techniques? Because placing a microphone or an airflow detector directly at the glottic level is invasive. It's more practical to detect the signal at the mouth after it has been filtered by the vocal tract. By filtering, we mean a spectrum of the frequencies from the glottal airflow has passed through the filter, the vocal tract, to produce an output at the mouth after some frequencies has been enhanced and other has been attenuated, some selected frequencies from the given spectrum. And then we use the signal obtained from the mouth and try to inverse the filtering process using the technique of inverse filtering, basically undoing what the vocal tract had did to the glottal signal in order to leave the original glottic signal as pure as possible. Either the acoustic pressure radiated from the mouth or the acoustic flow at the mouth can be inverse filtered to obtain an estimate of the glottal airflow waveform. The upper trace here shows a typical glottal waveform as suggested in the LF model. It demonstrates the airflow in liters per second as it increases and decreases during a vibratory cycle. The lower trace shows the acceleration and the deceleration of the flow, the increase and the decrease of the velocity of the changes in the flow itself. A typical cycle would have three phases, starting with the open phase. In the opening phase here, the airflow starts flowing through the glottis. The glottis is open and the airflow is passing here until it reaches a maximum. During the increase in the flow, there is also a mild increase in the acceleration of the flow. Until this point is reached, when there is maximum flow here, the vocal folds starts to close back again, and this is followed by a decrease in the flow with a more increase in the deceleration compared to the acceleration. Until this point is reached, the maximum dip corresponds to the point of the glottal closure instant. The glottis closed up here. This will be by an abrupt movement of the vocal folds. This will be followed by some flow here, little flow after the glottis has closed, and then the closed phase would start with no flow as the glottis is now closed completely. So these are the main three phases, the opening phases during which the glottis is open with flow and acceleration of the flow. A closing phase, the vocal folds are starting to close back the glottis with decrease in the flow and a more prominent deceleration of the flow until the point of the glottal closure instant, and then it's followed by a return back to the baseline with only a little flow in the start of the in the end of the closing phase before starting the opening phase. These charts here would demonstrate the similarities and the differences between the glottal flow waveform, the bottom trace in here, and the glottal area waveform as registered from an electroglottogram in the second trace in here. You could see the obvious similarities between the two traces as expected. The shape of the flow rate generally follows that of the glottal area opening. As the glottal area increases in size, then the glottal flow would also increase. As it starts decreasing in size, the glottal flow would also decrease. So there are some obvious similarities, but there are also some interesting differences. You could see two of them here, the shift of the peak of the glottal flow to the right in relation to the peak of the glottal area waveform, and this peak in here during the glottal closure, the area stayed at the minimum value, but the flow rate did not stay at the minimum value, but rather has this peak. These differences are mainly related to the acoustic coupling, the interaction between the voice as the source and the vocal tract as the filter. This non-linearity and the relation between the source and the filter can explain some of the differences between the glottal flow and the glottal area. To explore this non-linearity and the relation between the source and the filter, the glottal area waveform reaches a peak earlier than the glottal flow waveform. This is due to the skewing of the glottal flow waveform to the right in here. The cause for this skewing and the delay in reaching the peak is the inertia of the air mass just above the vocal folds during phonation, which causes a delay in the increase in the glottal flow during the opening phase of the glottal area, and also a more rapid decrease in the flow during the closing phase of the glottic area. So this shift to the right is a manifestation of the interaction between the source and the filter and their non-linear relationship. Several parameters can be extracted from the glottal flow waveform, and these parameters can have some clinical implications. Some of these parameters are related to the duration of the phases of the glottal flow waveform. Others are related to the amplitude of parts of the waveform or its time derivative. Starting with the duration related parameters, we've seen that a typical glottal flow waveform is divided into three phases: the closed phase, the opening phase, and the closing phase. Now, the open quotient is the sum of the opening phase and the closing phase divided by the total duration of the cycle. During this part, during the open quotient part, the glottis is open. It's opening here and it's closing here, but there is some flow during these two phases. The sum of these two divided by the total time for the cycle gives the open quotient. The closing quotient is only this part in here, the closing phase divided by the time of the whole of the cycle. There is another parameter here, the skewness quotient. This would refer to the degree of the skewness of the curve, usually to the right. You would have a slower ascent than a more abrupt descent of the flow, and this skewness here can have clinical implications. The skewness is the opening phase divided by the closing phase. So rather than adding them together, we're dividing the opening phase in here by the duration of the closing phase to give the skewness quotient or the speed quotient. This skewness quotient, which is defined by the duration of the acceleration divided by the duration of the flow deceleration, ranges between 1.1, where the two are almost equal, the duration of the acceleration and the duration of the deceleration, to 3.4 when the opening phase is as much as 3 times the duration of the closing phase due to the abrupt closure of the vocal folds. So the physiological range would be this 1.1 to 3.4. A higher value than this would indicate that the flow decreases very rapidly in the closing phase, which will lead to a higher vocal intensity. This is usually related to hyperfunctional dysphonia. The glottal flow skewing to the right is just one of several indicators of a strong source-filter interactions. These interactions would suggest that the relationship between the source and the filter is not linear. Rather, it's a non-linear with feedback from the filter affecting the source as well. This interaction can happen at least at two levels. The first level is the interaction caused by the vocal tract, the filter pressure on the glottal flow, as we have seen. And the second level is the interaction of the filter, the vocal tract, on the vocal cord tissue movements. So the interaction affects the tissue movements of the vocal folds itself in level 2 and affect the glottal flow in level 1. In glottal flow, there are two examples of them. One is the glottal flow skewing, the delay in the peak of the glottal flow relative to the peak of the glottal area, and the other is the ripple component in the glottal opening phase. We've been through some of the parameters describing the glottal flow waveform related to the duration of some of the phases of the glottal flow waveform, things like the open quotient, the closing quotient, and the skewing quotient, all related to durations of the phases. There may be some difficulty in the exact identification of the start and the end of the different phases due to some impurities in the estimated signal while inverse filtering it. These impurities would allow some indecisiveness in the identification of the exact moment of the start and the closure. If there is incomplete cancelling of the formants, the effect of the filter on the signal is not completely removed. The exact start and end point of the phases can be difficult to identify. That's why another set of values related to the amplitude rather than the duration of parts of the glottal flow waveform or its time derivative can be of value. Things like the maximum flow obtained from the glottal flow waveform and the maximum airflow declination ratio obtained from its time derivative. This is a chart of the glottal flow waveform and its time derivative here on the lower tracing. The negative peak of the time derivative of the glottal flow in the closing phase of the flow is much more dominant than its positive peak in here. This is very dominant and clear. The instant of the most negative peak is considered the point of main excitation of the vocal tract. And the corresponding negative peak in here is referred to as the maximum flow declination rate. This is a measure determinant of the peak amplitude of the produced voice. This is a computer-generated diagram of modeling of the different factors that interplay during a vibratory cycle of the glottis, including the glottic area waveform, the glottic flow waveform, and the intraglottic pressure. The glottic area waveform would depend on the smaller of the two entities, the glottic entry or the glottic exit in the glottic canal. So the lower of the two will determine the glottic area. They will be equal, the glottic exit and the glottic entry, at the peak of the glottal area waveform in here when the configuration of the vocal folds change from convergent to divergent. This would be the peak of the glottal area here. The glottal flow waveform would have a peak that is shifted to the right, skewed to the right in relation to the glottal area waveform, as we have described earlier, due to the vocal tract air inertia. There are other manifestations of the interaction between the source and the filter in the glottal flow, and that there is a rapid declination here of the glottal flow, and there are some ripples at the opening of the glottal flow. All these manifestations plus the shift of the peak to the right are due to the interaction between the glottic signal and the filter, the vocal tract filter. You would also notice that the intraglottal pressure does not reach the zero level when the vocal, with the peak of the glottal area, when the glottic canal is fully open. It actually reaches the zero level at the peak of the glottal flow rather than the peak of the glottal area waveform before going into the negative pressure in the divergent phase of the glottal cycle. The duration of the open phase in relation to the total duration of one vibratory cycle gives the glottal open quotient. This has its effect on the voice source spectral slope. If this ratio lies between 0.4 and 0.7, as in normal voices, if it is less than 0.4, it usually indicates a pressed voice, and if it is more than 0.7, it's associated with a breathy and weak voice. This voice source spectral slope graph comes from the fact that the harmonics produced by the voice source changes as the frequency increases. This rate of change of the harmonics when the frequency increases gives the spectral slope. The lower harmonics here, the lower frequencies, are affected by the increase in the glottal open quotient. If you have a high glottic open quotient, like more than 0.7, then you would get a higher dominant first harmonic and a breathy and weak voice. And conversely, when the open phase is short, this would cause most of the glottal flow changes to occur within a smaller duration. This leads to energy boosts in the low frequency portion of the source spectrum. The shortening of the open phase would, in contrast, makes the second harmonic or even the fourth harmonic more dominant, and this would give a pressed voice quality. The glottal flow waveform and its time derivative waveform shows clearly the vocal fold closure is much faster than the vocal fold opening. This abrupt vocal fold closure determines the amount of energy in the acoustic spectrum and would show a slowly reducing spectral slope rather than a sharp decrease in the spectral slope. The overall number of the harmonics is also be influenced by this abrupt closure, and the amount of energy in the high frequencies can all be affected by the decrease in the duration of the vocal fold closure. The time taken for the vocal folds during its abrupt closure to close up the glottis is termed TA and can be calculated from the glottal flow chart and its time derivative in this time in there. This period, if it is shortened, if you have a very abrupt closure of the vocal folds, would result in a bright voice which projects well, as we have just seen. On the other hand, if there is incomplete closure of the glottis or slow vocal fold closure resulting from, say, a pathology or paralysis, this would result in less energy in the acoustic spectrum and fewer higher harmonics. This will result in a breathy voice that is not going to project well. By this we come to the end of this presentation on the physics behind the voice production and analysis. Assalamu alaikum.